In the previous video, Demystifying Imaginary Numbers, I made a few comments that I'd like to follow up on in this video. Okay, this is going to help us get closer to a thorough understanding of the square root of -1. The first comment I made had to do with the multiplication rules for the plus or minus operators, where I claimed that the square root of -1 had more to do with the operator and less to do with the 1. The second comment I made had something to do with the imaginary unit definition on the Wikipedia page, where it says there are two complex square roots of -1, I and minus I, which is what I have been saying all along, just as there are two complex square roots for every real number other than 0. Okay, so the key word here is complex. So both the real numbers and the imaginary numbers have complex square roots. And of course, if you've been following my YouTube channel, you'll know that when I am dealing with complex numbers, I implement them as a 2x2 matrix. But for the sake of this discussion, I'm going to word this a little bit differently. So I'm going to say that there are two complex square roots of -1, positive I and negative I, just as there are two complex square roots of +1, okay, +1 and -1. Okay, so I'm going to put the emphasis on the operator, which means that every time I write a positive number, I have to put a plus sign in front of it, okay? And as you may recall, in the previous video, I talked a little bit about the anatomy of a number. Okay, so in that section, basically what I did was I decoupled the operator, the plus or minus operator, from the quantity. Okay, we talked about quantities, which are magnitudes, which are entities that you can count maybe. So quantities, I decouple the quantity 9 from the positive and negative sign. And I also wrote in the identity. The identity is, you cannot operate on the identity. It is just a kind of a placeholder so that we can distinguish between real and imaginary numbers. And normally we don't write the R, normally we write the I. So when we want to identify imaginary numbers, we'll write 9I. And if it's positive, we won't write positive, but I'm going to write positive, I'm going to write negative, and I may or may not put them in brackets. I'm just doing it here now to show you that I'm decoupling the positive and negative sign from the quantity. And so when I definitely want to distinguish between the operator and the quantity, I will be writing it like this. So I will put the quantity in curly brackets. So here are the multiplication rules for the operators, for the plus and minus operators. You've got plus times plus is equal to plus, minus the minus operator times the minus operator is equal to the plus operator, and therefore the square root of the plus operator is the plus operator and or the minus operator, okay? On the right here, we have the operations that create a minus operator. So we have a plus operator times a minus operator is equal to the minus operator, and the minus operator times the plus operator is equal to the minus operator. Okay, so when you try to take the square root of the minus operator, you cannot do this using this information alone. So using the multiplication rules for one-dimensional numbers, I guess you can say, for real numbers, you cannot find the roots of the minus operator. So I just want to take a second here and talk a little bit about terminology, because in the previous video, I used the word solution interchangeably with the word root. Sometimes I use the word solution, I use that more than I use the word root. Technically, when you're taking the square roots, you're finding roots, which are solutions. So solution is a more general term for this kind of operation. And so I just want to make it clear because someone seemed to be confused about my use of the term solution. So I'm going to try to use the word root instead of solution when I'm talking about square roots. Okay, so sorry for any confusion that may have caused some people. Again, as I always say, the problem is with the language. And although it is correct for me to use the word solution, I think if it confuses someone, then I should stop using that word. And so I'm going to use the word root. There are two roots to the positive operator, plus operator and minus operator, and we cannot determine the root of the square root of the minus operator because there is no operation, at least not in the one-dimensional real numbers, there is no operation where you can square something and end up with -1. So this is where this information comes in, because this is saying that there are two complex square roots for both +1 and -1, and I implement complex numbers as 2 by 2 matrices. So another way of saying this is that the square root of both -1 and +1 produce a 2 by 2 matrix. Okay, so you're basically, when you take the square root, you are producing a square matrix. So in terms of the anatomy of a number, I'm going to write +1 like this and -1 like this. And so basically what I'm doing is I'm going to decouple the positive and negative operator from the quantity we call 1. So the square root of the quantity 1 is just 1, not plus or minus 1. We are actually going to be, since I decoupled the positive sign here, I'm going to take the square root of the operators independent of the quantity. So the square root of the quantity 1 is 1. The square root of the quantity 9 is 3, and the plus or minus is going to come when we do take the square root of the operator. So we're taking the square root of the operator independent of taking the square root of the quantity. So another way of saying this is the square root of 1 is plus or minus 1, not because of the 1, but because of the operator. Okay, the square root of the positive operator. Okay, the square root of the positive operator is the positive operator and or the negative operator. Okay, so the reason I'm doing this is to show you that the problem of the square root of -1 has to do with the operator and not the quantity 1. So when we go back to the multiplication rules for operators, we found that the square root of the positive operator was the positive operator and the negative operator because plus times plus equals plus and minus times minus equals plus, the plus operator, okay? And so, but the square root is also complex. So the square root of a real number, the square root of +1 is a complex number, and I implement complex numbers as 2 by 2 matrices. Okay, so the square root of the positive operator is the positive operator and or the negative operator, and in 2 by 2 matrix form, it looks like this. Okay, so the positive operators are on the forward diagonal, and the negative operators are on the forward diagonal, and they have the same sense. Okay, why do they have the same sense? Because plus times plus is plus, and minus times minus is plus. Okay, so when you take this matrix and you square it using the multiplication rules for multiplying 2 by 2 matrices, you're going to end up with the positives on the forward diagonal, okay? And when you multiply this, when you square this matrix, okay, if you square this matrix, then you're going to end up with, so negative times negative is negative, you're going to end up with positives on the forward diagonal. So both when you square this matrix and when you square this matrix, you're going to end up with the matrix with the positives on the forward diagonal, the positive operators on the forward diagonal. But in order to calculate a negative operator, you need to multiply the positive operator by a negative operator, and then you get a negative operator. So when you multiply a negative by a positive or a positive by a negative, you get a negative operator, okay? So, but there is no real solution. There is no one-dimensional solution to taking the square root of the negative operator. But we know that the square root of -1 produces complex roots, okay? Complex, they have complex solution. And of course, the complex solution is going to be a 2 by 2 matrix. So, although there are no real one-dimensional solutions to the square root of -1, there are two-dimensional solutions to the square root of -1. There are complex solutions, which are two-dimensional 2 by 2 arrays. And so the complex solution to the square root of -1 is 1 and -1 on the backward diagonal of the 2 by 2 matrix, okay? And the second one, so this would be -I, would be minus and plus on the backward diagonal of the 2 by 2 matrix. So again, although there are no real one-dimensional solutions to the square root of a negative number, there are two-dimensional solutions. One where you have the positive sign and negative sign on the backward diagonal, and one where you have the negative sign and the positive sign on the backward diagonal, as I show here. So as you can see, when we decouple the positive and negative operators from the primitive numbers, it becomes very clear that the problem with the square root of -1 has nothing to do with the numerical value, the primitive number 1, and has everything to do with the operator. Okay, so you can take the square root of the positive operator and get real one-dimensional real solutions, but you cannot take the square root of a negative operator and get a real one-dimensional solution. And you can see right here, when you take the plus and the minus, plus and times minus equals minus, and minus times plus equals minus. So it's almost as if you need a number that is simultaneously positive and negative to get a square that equals -1. Okay, so, and that's why you need in a two-dimensional solution, you have a number that can be simultaneously positive and negative, and then when you square this number, you get, when you square this matrix, you get this matrix right here. And so, as we talked about earlier, that both the square root of +1 and the square root of -1 produce what we refer to as complex solutions. And in the language that I'm proposing here, the complex solution can be implemented as a 2 by 2 matrix. And so you have both the square root of +1 and the square root of -1 producing square matrices, which literally correspond to complex numbers. Okay, complex numbers are 2 by 2 matrices. The real component, if you want to call it that, occupies the forward diagonal, and the imaginary component occupies the backward diagonal. And because of this, the real and imaginary numbers can coexist. So I can actually add an imaginary number to a real number to the real component of a complex number. This is really a complex number. So when you add the complex number that has only a forward diagonal and a complex number that only has a backward diagonal, okay, these values, these operators can coexist. Okay. And so next what I'm going to do is I'm going to put the ones back in. Okay, so I'm going to put ones at least into the matrix. So now we're talking about the square root of +1, and we're talking about the square root of -1. Okay, so the square root of +1 has ones on positive ones on the forward diagonal, or it can have negative ones on the forward diagonal. And this matrix here squared is equal to this matrix, and this matrix here squared is equal to this matrix. Okay, This matrix here is referred to the identity of the 2 by 2 matrix. So this is the identity matrix. We would call it the identity matrix of the 2 by 2 matrix, okay? And this is the negative of the identity matrix. So this squared is equal to this, and this squared is equal to this. So now, but there is no positive solution that will give you the negative matrix. To get the negative matrix, you need the square root of -1. Okay, in the square root of -1, you have plus and minus in the backward diagonal. So you can either have plus here and minus here, or you can have minus here and plus here. This squared produces this matrix here, the negative matrix, which this is the symbolic language now for the -1 2 by 2 matrix, complex matrix. Okay, so this squared produces this matrix, and this squared produces this matrix, okay? So this squared produces this matrix, this squared produces this matrix, the identity matrix. This squared, okay, produces this matrix, the negative identity matrix, and this squared produces the negative identity matrix. So symbolically, okay, we can write the square root of -1, but in reality, we need to write this matrix here. The square root of -1 produces two complex solutions. Square root of -1 produces I and minus I. I and minus I are complex numbers. I and minus I are not real numbers. They're not even imaginary numbers. I and minus I are complex numbers. So the square root of -1 produces two complex solutions, I and minus I, and the square root of +1 produces two complex solutions, which we loosely refer to as 1 and -1. Okay, so square root of +1 produces 1 and -1. Okay, and but technically under the hood, the square root of +1 produces this matrix and this matrix, because complex numbers are two-dimensional numbers, and two-dimensional numbers require two-dimensional arrays to be implemented when you are, say, writing a computer program. So when you're writing a computer program, the best way to implement complex numbers is with a 2 by 2 matrix. Okay, so hopefully you can see that. And of course, these blank regions here actually contain the value 0. I left them out. 0 is neither positive nor is it negative, which is why I didn't put it into these matrices, but I'm going to put them in here. When you put them in here, you see that now the matrix is full. This is a positive number, this is a negative number, this is an imaginary number, and this is an imaginary number. But technically, when you do things this way, all you have is forward diagonal and backward diagonal. You don't actually need to talk about real and imaginary numbers. We can say that the forward diagonal is real and the backward diagonal is imaginary, but if I were teaching this from scratch, I would ignore the whole language, those words real and imaginary, and I would use the terms forward diagonal and backward diagonal, and then a lot of the confusion, I think, will go away. So algebraically and symbolically, if you're not writing 2 by 2 matrices, you kind of have to use those terms, but when you're talking about the 2 by 2 matrices directly, you don't actually need to invoke the real and imaginary terms. You can just start from here and move forward. So that's what we're going to do. We're going to start from here and we're going to move forward. So as I said previously, the identity of the complex number is the identity matrix. So this is the identity of the complex numbers. The forward diagonals have to be +1 to be the identity of the complex numbers. So the identity of a number is a number that when multiplied by another number leaves that number unchanged. So since complex numbers are two-dimensional numbers, and that can be represented as a 2D array, okay, this number here is not like two numbers or four numbers. It is literally one number. This is a complex number, and this complex number is a 2 by 2 matrix, a 2 by 2 array that has positive ones on the forward diagonal. And so if you take another 2 by 2 matrix, any 2 by 2 matrix, doesn't even have to be a complex matrix, any 2 by 2 matrix, and multiply it by this matrix here, you're going to get back the original matrix. And so that is by definition the meaning of the identity of a number. And of course, I know previously I referred to I and minus I as identities, and that is technically not correct because it should be called a unit, and that's what it's called on the Wikipedia page. And so I wanted to clarify that now. I call I the identity of the imaginary number because when you put a little I beside a number, that identifies that number as an imaginary number, but technically it's not an identity by this definition because when you multiply, this is the only 2 by 2 matrix that acts as an identity from this definition here. Okay, so I wanted to clear that up because I realized that I do often say that I is the identity of the imaginary numbers, and literally there is no imaginary number. Okay, imaginary numbers are complex numbers, and the identity of the complex numbers is this matrix right here. So basically what I'm saying here is that imaginary numbers don't exist as one-dimensional numbers, as like a number line that you would have with the real numbers. We can have a real number line and never invoke any other dimensionality to it. The real number line is literally a line, but there is no such thing as the imaginary number line. Even though we can imagine one, I can actually write an imaginary number line and make it look like there could be an imaginary number line, but technically when you take the square root of -1, you get a complex solution, and you get a complex number, a two-dimensional number, and there is no such thing as the identity of the imaginary numbers other than through the other definition I had where the I identifies a number as an imaginary number. Okay, so once you take the square root of -1, you get imaginary numbers that are complex numbers. And the identity of the complex number is this guy right here. Okay, the identity of the complex numbers is the identity matrix with positive ones on the forward diagonal. So let's go back to the imaginary unit of I and see if we can explain it a little better. Okay, so the imaginary unit I is defined solely by the property of its square. So solely by the property that its square is -1. So the imaginary unit is defined solely by the property that I squared is equal to -1. Okay, so this is a definition. We predefine I as I squared is equal to -1. Okay, so why? Okay, why is I squared equals -1? Or more specifically, y is positive I squared equal to negative I squared equal to -1. So y is positive I squared equal to -1, and y is negative I squared equal to -1. Okay, and so this is easily answered by looking at the matrix forms. Okay, this is +1 in the complex, so I is not an imaginary number. I is literally a complex number that occupies the backward diagonal of a 2 by 2 matrix. So, and I'm defining this as I in my in the standard that I'm developing. I define this as I. Okay, so in my standard, I squared is equal to this matrix squared, which is equal to the negatives on the forward diagonal, which is -1 in complex numbers. So in the complex number language, if I write -1, I really mean negatives on the forward diagonal. If you want to call it real, you can call it real. So I squared is equal to -1, where -1 is a complex number and with minus signs on the forward diagonal. Okay, with -1 on the forward diagonal. So if you take, and this is minus I, so minus I is I times -1, so now you have -1 here and +1 here. When you take this matrix and you square it, you get the negative matrix, the negative identity matrix here. Okay, so this is the true meaning behind I squared equals minus 1. Why does I squared equals minus 1? Because I is a complex number, and when you write it out in full in the 2 by 2 matrix form, you write it like this with zeros on the forward diagonal, so there's no real component, and you write the ones on the minus, backward diagonal with the plus and minus signs, and you end up with this matrix here. Okay, so this is under the hood. I squared equals minus 1 can be explained with this procedure right here. So the next question we want to answer is this, okay, imaginary rotations. Okay, so we're talking about quarter turn rotations here. And so when multiplied by the imaginary unit I, any arbitrary complex number in the complex plane is rotated by 1/4 turn, okay, or pi over 2 if you want, radians, or 90 degrees if you like, okay, anti-clockwise, okay. When multiplied by minus I, any arbitrary complex number is rotated by a 1/4 turn clockwise, okay. So I generates a 1/4 turn counterclockwise, and minus I produces a 1/4 turn clockwise. Okay, so the question I have is why? Why does the imaginary unit I create these 90-degree rotations? Why? What is special about I that makes it rotate 90 degrees? And what does that mean to rotate a complex number clockwise and counterclockwise in the complex plane? Okay, what does that mean? So in order to explain this, we need to talk about coordinate systems, okay? So on the left here we have what's called the complex plane, and in the complex plane we have the real component on the horizontal, and positive real is pointing to the right, and we have the imaginary component on the vertical axis, and positive I points up. Over here we have the standard two-dimensional Cartesian coordinate system with x on the horizontal and positive x pointing to the right, and y on the vertical with positive y pointing up. So what is the difference between these two coordinate systems? What is the difference between the complex plane and the standard Cartesian coordinate system? Okay, so the answer I'm going to give you right now is absolutely nothing. There is nothing difference between these two except for the labeling of the axis. So here I'm saying R and I, and here I'm saying X and Y, but there is literally and mathematically no difference between these two representations, as I will show you in the next couple of slides. So before we move forward, let's just read this again. This is what we're trying to explain. When multiplied by the imaginary unit I, any arbitrary complex number in the complex plane is rotated by a 1/4 turn or 90 degrees counterclockwise. When multiplied by minus I, an arbitrary complex number is rotated 1/4 turn clockwise. Okay, and so my question here is why? So what we're going to do here is we're going to place a point in the complex plane at the position 1, 0. So what that means is the real component is going to be 1 and the imaginary component is going to be 0. Okay. So now what we're going to do is we're going to multiply this point by I. Okay, so what they're saying is that when you multiply the point by I, the point is going to move from here, okay, to over here. Okay, you're going to get a 90-degree rotation from this location here, okay, this location here to this location here. So that is literally what this is saying. When you multiply any arbitrary complex number, okay, this is a complex number, this is a complex point, it's a point in the complex plane is a complex number. When you multiply that by I, you get a counterclockwise rotation that brings the point to here. And so this new number, let me just do this here. Okay, let me get rid of that. Okay, this new number is going to be 0 and 1 in the complex plane. Okay, so I'm just editing my PowerPoint here live. Okay, so when you take a point from 0, 1, okay, let me make this a bit smaller. When you take a point from 0, 1, 0, okay, from when you take this point 1, 0 and multiply it by I, that moves the point, okay, to here. Why? Okay, why does it do that? So next, what we're going to do is we're going to place the same dot onto the Cartesian coordinate system where we have x on the horizontal and y on the vertical. Okay, so they are just labeled differently than this one here. I'm going to place a point at 1, 0 where x equals 1 and y equals 0. So then, instead of using this mysterious letter I, where we just assume that it is a counterclockwise rotation and minus I is a clockwise rotation, what I'm going to do is I'm going to define positive I as this matrix here and negative I as this matrix here. And so when you take this point 1, 0 and multiply it by this matrix here, okay, what I'm going to do is I'm going to actually copy this matrix and put it into my PowerPoint here so you can see it. So when you take this point here, 1, 0, and multiply it by this matrix here using a very specific convention, I actually use row convention, and so when you multiply this point by this matrix, you get a counterclockwise rotation, same as when you multiply the point by I. This is my I, and so now when you multiply this point by this matrix, you get the counterclockwise rotation, 90-degree counterclockwise rotation that brings the point from positive x, the positive x-axis, to the positive y-axis. So this is functionally identical to what I is supposed to do, only here we're much closer to the truth because we don't have like this imaginary letter that we don't know what it is. We have something where we do know what it is. This is a 2x2 matrix where every entry in the matrix is a ponderable value. Okay, it is a value that I can plug into the computer. I cannot plug I into the computer. If I plug I into the computer, it's going to think I mean the letter I. When I plug this into the computer, when I generate a matrix with this value, I can actually use it in my computer graphics. If I need to rotate a point counterclockwise by 90 degrees, that is what this will do. But this still doesn't solve all the mysteries because we still have to ask the question, why? Why does this matrix produce a 90-degree rotation from this axis to this axis? And just to be clear, if we apply this matrix again, it brings it to here, and if we apply this matrix again, it brings it to here, and if we apply this matrix again, it brings it to here. So this is similar to the I, where we've got, if you multiply by I, it brings the point to here, and then if you multiply by I again, it brings it to -1 on the real axis, and then if you multiply by I again, it brings it here and brings it here. So this this exactly functions the same as I, only this is more understandable because this is a transformation matrix. This is something I'm familiar with in computer science, okay? So the only question we now have to answer is, why does this matrix with ones on the backward diagonal with opposite sense produce 90-degree rotations in the Cartesian coordinate system? So to answer this question, I'm just going to change things up a bit and rearrange the screen to look like this. We have the Cartesian coordinate system here. We've got the I and minus I transformation matrices. So now I can identify these as transformation matrices. When you take this point and multiply it by this transformation matrix, it brings the point to here. And when you multiply it by this, the I matrix again, it brings it to here. And when you multiply it by I again, it brings it to here, and so on. Okay, so if you use the I minus matrix, the point would start here. If you multiply by the I minus matrix, it's going to bring it to here. And so it's going to go in the opposite direction. Okay, so the way I set up my system, the way I set up my convention, is this matrix here corresponds to I, which corresponds to counterclockwise rotations, 90-degree counterclockwise rotations, and this matrix here corresponds to 90-degree clockwise rotations. Okay, and so the question that we're asking now is, why do these matrices produce 90-degree rotations? And the answer, the simple answer and the only answer, is that these two matrices here are these matrices in disguise. Okay, so the this I plus matrix with +1 and -1 on the backward diagonal and zeros on the forward diagonal corresponds to this matrix here, where you have the cosine of 90 on the forward diagonal, and you have the sine of 90 degrees on the backward diagonal, and the cosine of 90 is 0, okay, and the sine of 90 degrees is 1. Okay, so that's why we have zeros on the forward diagonal and plus and minus 1 on the backward diagonal. So you still have the plus and minus, the signs are the same, but now we can clearly see why these two matrices produce 90-degree rotations, because this is this matrix in disguise. So now we have a clear explanation for why when you multiply by I, you're really multiplying by this matrix, but this matrix here is really this matrix in disguise. And so you have a cosines on the forward diagonal with the same sense. You have the sine of 90 degrees. The important point here is 90 degrees. Why does this produce a 90-degree rotation? Because we're telling it to go 90 degrees. Okay, in the minus I, it goes in the opposite direction, but it is going 90 degrees because we are telling it to go 90 degrees. We're saying, what is the cos of 90? The cosine of 90 is 1. Sorry, the cosine of 90 is 0. That's why there's zeros here. And the sine of 90 is 1. Okay, and that is why there are 1s here. Okay, so I and minus I are subsets of a more generalized 2x2 matrix where we can plug any angle into here. Okay, so the generalized version of what we have here, okay, the generalized version of this is where you just put a theta, so you have cos of theta and sine of theta. This is no longer I, so this cannot be I. I'm going to take this out. Okay, this is no longer I because it's only I when the angle is 90 degrees. Okay, so I, when you multiply a number by I, it brings it 90 degrees, 90 degrees, 90 degrees. But the more generalized form of this transformation matrix is this matrix here. Again, let me get rid of these, which is basically Euler's formula in disguise. So this is the 2x2 matrix version of Euler's formula, cos theta plus I sine theta, and this is cos theta minus I sine theta. Okay, so these are the complex conjugates of each other. This can be implemented on the computer directly. Okay, this cannot, because my computer does not have an operator, does not have an I number or an I operator or an I. I cannot plug I. If I plug I into the computer, it's going to think I mean the letter I. There is no mathematical operator or symbol for I in my computer. Basically, I need to do this. So when we do it this way, we no longer need, I'm going to get rid of it, we no longer need the concept of I or R, real and imaginary. All we need is the X and Y Cartesian coordinate system. Okay, I'm going to put this back here. Okay, get rid of that. So all we need are these transformation matrices and the Cartesian coordinate system to rotate a point any angle, not just 90 degrees. Okay, so this matrix here will rotate a point any angle, any angle. Okay, it could be 1 degree, it could be 10 degrees, it could be 90 degrees, it could be 180 degrees, it could be 270 degrees, 360 degrees, it could be, you know, whatever degree you want. Okay, so this is the generalized version of complex numbers in 2x2 matrix format, where you don't need the concept. We can actually ditch the concept of real and imaginary. We don't need it to do the math. Okay, we don't need it to do these operations. Okay, this is basically all you need. In fact, this is basically all you need to do all of the stuff that I showed you, all of the helix wave animations and all of Yonel Dinyu's animations. I used these transformation matrices. The main purpose of this video, of course, was to demystify the square root of -1. So let's see if I succeeded. Okay, we start with the square root of -1. The square root of -1 has two complex roots referred to as positive I and negative I. Okay, so positive I and negative I are actually not of much use to me in the computer. I need more information. And so what I realized is that positive I and negative I are complex numbers, and complex numbers are 2x2 numbers. They're 2x2 matrices. And so positive I in the 2x2 matrix form has ones on the backward diagonal with opposite sense. And negative I also has ones on the backward diagonal with the opposite sense, but they are the inverse or the negative of what you see in the I matrix. So this is the I matrix, the positive I matrix, and this is the negative I matrix. And as we know, when you multiply I, you get a 90-degree rotation, a counterclockwise 90-degree rotation. And we know you multiply a point by negative I, you get a clockwise 90-degree rotation, so the opposite rotation. And you see the same thing with these two matrices. So we know these two matrices correspond to 90-degree rotations. And the reason this happens is because these matrices are these matrices in disguise. Okay, so this matrix zeros on the forward diagonal. There's zeros on the forward diagonal because the cosine of 90 is 0. So this is actually the real matrix. This is I right here. This is I, and this is minus I. This is I, positive I, which I refer to as positive I in my standard, and this is negative I in my standard. And when you multiply a point by this transformation matrix, you get a counterclockwise rotation. And when you multiply a point by this transformation matrix, you get a clockwise rotation. So this explains why I rotates, for one thing, and explains why I rotates by exactly 90 degrees. So this is I plus I, and this is minus I, fully, completely transparent with no ambiguity and no, let's say, algebraic symbolic confusion. Okay, this also does the rotation. So when you solve this matrix here, you get this matrix here. That's why this matrix behaves like this matrix, because this matrix is the solution of this matrix. So cos of 90 is 0 and sine of 90 is 1. And so this is the complete, most transparent, least ambiguous interpretation of the square root of -1 that I can think of. Okay, so I hope this helps you to understand what's going on here. You don't need any of this in the middle here. All you need is this and this to do all that cool stuff I was doing with those helix waves and the ether circulation model. I can model things using this, and I also use this in the advanced robotic devices that I work on, the medical devices. I use exactly this, okay? I don't need any other mathematical tools I don't even use quaternions. I use this. Okay, so I will talk about that in a future video. That is super interesting, but the main point of this video was to demystify the square root of -1. So what I'm going to do later on is I'm going to put up a poll on the community section, and I'm going to, in that poll, if you watch this video, I want you to go there and I want you to tell me whether I succeeded or not in demystifying the square root of -1 for you. So I think that'll be kind of fun. I don't know what the results will be. I understand this myself, and I really want other people to understand it too. So I hope I got through to some people, and I guess we will see. So yeah, so I'm going to end this video. I hope you enjoyed it, even if you didn't get everything I was saying. And this is really the nail in the coffin for me. This slide right here is really everything that I wanted to say, was trying to say over the years. This kind of encapsulates it all, okay? So anyways, I'm gonna go. Bye.